Here is a review of variance and standard deviation. As a reminder, what is variance? Variance measures how far away the values in our data are from their average value. So each individual value for a variable that we're interested in, how far away is that variable from the average of all of those values? We use it to capture the amount of variability in that distribution of values. For example, how much variability there is within a set of test scores for our students. Mathematically, it's the average squared difference between each value for the variable of interest and the mean of all those values. How do we get the variance? Let's break it down. Let's start by finding the mean of the values for the variable of interest. For example, if our distribution is 8, 9, 4, 6, 11. Let's say that's our age variable, and those are the ages of the kids in our group, in our sample. The mean for that group is 7.6. Then we're going to calculate all of the deviation scores. That is, how far each individual value x is from the mean. And you see my floating x bar is sort of fallen down there. I apologize. So then you see below that each value, and we are subtracting from it the mean, which is 7.6. So 8 minus 7.6 equals 0.4, 9 minus 7.6 equals 1.4, etc. And if we sum those differences without doing anything else first, you'll find that we get 0. Try it in an Excel spreadsheet on a calculator just to be sure, so you see that I'm right when I say that. And by the way, that's not just me saying that. So what do we do with that? If we just sum those and we get 0, we address that by going back and squaring each of those deviation scores. So 8 minus 7.6, which equals 0.4, we square that and we get 0.16. And we do that for each of those deviation scores. And then we're going to sum all of those deviation scores. So there's our nice sum symbol. And we take the average. That is, we divide by the number of individuals in our sample or our population. Does it matter if it's the sample of the population? As we talked about, yes, it matters. If we're talking about the population, then we use capital letter N. We use all of the number of individuals in our population. But if we're talking about the sample variance, we use little n minus 1. And perhaps, as you all were a little lost last night, and I did not help, so here we are today. If you feel still a little bit lost, we use n minus 1 because we are estimating the variance for a sample. We need to adjust the sample size in this way to get a less biased estimate of the population variance. Remember, this is an estimate because in reality, we're very rarely able to study an entire population. We are always making estimates based on a sample that we have drawn. In this case, we take away 1 and not a different number to indicate that we are estimating one parameter for our sample. And the parameter in this case is the variance. If we were estimating a different parameter, we would also use take away 1 degree of freedom. Later in the semester, you'll see that sometimes we take away more degrees of freedom because we are estimating multiple pieces of information. So let's keep going with the calculation of variance. This is where we left off. We have all of our squared deviation scores, and we said we were going to sum them, divide by the number of degrees of freedom, so n minus 1. There were originally 5 students in our group, and so that's now 4. So the variance, the sample variance, is 7.3. And as you'll see, the variance is always going to be positive. It's always going to range from 0 to positive infinity. It will never be negative because we've gotten rid of those any negative signs. It will always be positive. As a result, for the standard deviation, we also see that it will never be negative. The standard deviation, S, is the square root of the variance, S squared. And because the variance can never be negative, the standard deviation will never be negative. The variance and the standard deviation can, however, be zero if all the values in the distribution are the same. For example, in the case of how much the federal government reimburses schools for each student who receives free lunch. In each year, that reimbursement is the same across all students. This means there is no variability, and therefore there's no deviation from the mean to measure.